All right. So we have been talking about systems with pretty much the spring mass damper. At the beginning, we talked about pendulum. We didn't get into uh, more examples about the combination of pendulums and springs. You saw, I guess, one or two in the homework problems. Now, I want to slightly start basically transitioning to a little bit more complicated systems, right? We're pretty comfortable at this point with the spring mass damper. We know that we can find the equivalent of pretty much good range of systems as the spring mass damper systems, and then, basically simplifying those systems or idealize those systems as a spring mass damper systems, and then study their behavior with a pretty relatively good um, accuracy, depending on what we are focused on and what we want to study. Now, what I want to do is I want to go slightly, as I said, I want to move towards more complicated systems. And before we do that, I have to review a specific concept that you have studied before, but my experience is that a lot of you forgot that by the time you get to this course. Most of you forgot that, so it's better to just refresh our memories about this concept, and then we move into again. So it's more like a, um, I would say, take a break from vibrations for half a class. I would say it's a little bit of math. We review this concept, which is basically concept of eigenvalues and eigenvectors. How can we find those? What are they, at least very briefly? And then we go back to vibrations, and in a class or two, you will see where we use these concepts and how do we use eigenvalues and eigenvectors, and how do they come into play when we are looking at vibrating systems. So here's what we're going to do today at this for the first part of the class. We're going to talk about eigenvalues and eigenvectors. Eigenvalues and eigenvectors. As I said, I'm hoping that you've seen these before, and this is not the first time you hear eigenvalues and eigenvectors. Please let me know if this is the first time you hear these names. But probably in some math course a while ago. Now, what are they? Well, we are mainly focused on their applications in vibrations, but we're going to briefly touch on what they are, and generally speaking, what when do they appear? Let's say. Now, what is an eigenvalue or what is an eigenvector? They're tightly related. Now, think about that. You have a matrix, right? And that matrix acts on a vector. So let me put it this way. Let's say I have a matrix there. Think about it as this is a box. I have a matrix A, some matrix A. It multiplies vector X, or this matrix acts on vector X. Let's say we have vector X in. Vector, somehow I didn't manage not to fit it there. Vector X comes in. Goes out another vector. Goes in a vector X, goes out vector AX. Vector X goes in, vector AX goes out. So the idea is very similar to functions in calculus. You have X comes in, Fx comes out. You had function in calculus. That function was operating on inputs. Now in this case, instead of the function, this is not calculus, this is linear algebra. So the function, you replace the matrix X, matrix A. the input, whatever x, is vector x. So vector x comes in, matrix A does some operation on that, or it multiplies. We're to say in this case the operation is straightforward. It x multiplies A and goes out vector ax. Very similar to a function in calculus. Now, I'm specifically, so this is general case. Now, I'm specifically interested in vectors that come out, like ax vectors, that have the same direction as the vector that goes in as x. Right? So this is a special case. It's a special case. It's not very typical. Vector x comes in, matrix A does an operation, multiplies, or vector x multiplies A, and then vector ax goes out. Now, in this general case, I'm interested in a special case. It's not typical that the outcome, vector ax, is in the same direction as vector x. Now, when ax is parallel to x, then x is eigenvector. And it's as simple as that. Mathematically speaking, that is a special case that I said. Vector x comes out, x goes in, vector ax comes out. When ax, vector x, is parallel to x, x is an eigenvector. So let me just write it here. When ax is parallel to x, then x is an eigenvector. Now, since they are parallel, their magnitudes can be different. Right? So I can write it this way. Well, if this is the case, right, then I can write it as ax is equal to lambda x. I can write it better, lambda x. Well, let me just be consistent and use x. Ax and x are parallel, but lambda is just a constant. Because they're parallel, they can have different magnitude. I didn't say they have the same length, so the length can be different. Like the vector x can be multiplied by some constant, it can be bigger than ax, smaller than, the same size, depending on what lambda is. It can be in the opposite direction. Right? Can be, if lambda is negative, ax would be in the opposite direction of x, but they're still parallel. That's the only thing that I'm interested in, right? That's the only thing that the condition I put. So if I write it this way, right, so I defined eigenvector. This was eigenvector. If I write it this way, now lambda can be positive, can be negative, it can be even be zero. Right? If it's zero, it's a different story, but we're not going to deal with that. But it can be zero. In this case, then if I write it this way, the lambda is eigenvalue. So let's put this, lambda can be positive, negative, positive, negative, or even zero. And it's called eigenvalue. This eigenvalue. That's the general concept of eigenvectors and eigenvalues. So the idea is that we have some, we have some matrix A, we have vector x, as long as when vector x is multiplies vector x multiplies matrix A, and the output vector ax is parallel to x, then x is eigenvector, and if we can write them, the relationship between them, depending on what lambda we have to choose to construct that relationship, that lambda is eigenvalue. That's it. Now, how do we find eigenvalues and eigenvectors? So that would be the question that we are more interested in. This is the concept. Now, how do we find eigenvalues and eigenvectors? Or in this case, you can say, how can we find x and lambda? Let's just start with the equation we have. Right? Ax is equal to lambda x. I just move that to the other side. Ax minus lambda x is equal to 0. I can factor out x. A minus, well, if I factor out x, I have to use identity matrix to make this work. Lambda I x is equal to 0. Remember, identity matrix is just a matrix with values 1 on as its diagonal elements. Because lambda is just constant, I have to convert it into a vector, into a matrix. If I want to do the matrix operation, A is a matrix, can be 2 by 2, 3 by 3. And remember, all the matrices that we are going to talk about are a square matrix. So number of rows and number of columns are equal. Right? So it can be 2 by 2, 3 by 3, 4 by 4, 5 by 5. In order to make this work, I'll just say minus lambda I being the identity matrix. So let me just add it here. Identity matrix. All right. So now I don't know x and I don't know lambda. This is an equation that two things there are unknown. I don't know what A is, I don't know what lambda is. But one thing I know is that, let me write it here. I don't know x and I don't know lambda, right? None of them I should know. I want to find. But one thing I know, looking at that expression, a minus lambda I, the whole thing multiplied by x equal to 0. Now the outcome is either x is equal to 0 or a minus lambda I equal to 0. Now x being equal to 0 doesn't really give us anything, because if x is equal to 0, then this is always 0, and really nothing comes out of that. Right? This is something trivial. I'm not interested in that. But I know, let's put it this way, but I know a minus lambda I is equal to 0. Now, keep in mind that this a minus lambda I is a matrix. Right? A can be, as an example, I'm just going to erase it later on, but let's say A is a matrix as 3, 4, 1, 8, right? Minus lambda just being a constant, and I is identity matrix, 1, 1, 1, just for 2 by 2 matrices. So this becomes 3 minus 4 lambda, 4, 1, and 8 minus lambda. So this is a matrix. This is a minus lambda I. So keep in mind, this is a matrix with lambda there. Could be 3 by 3. Then the A would have been 3 by 3. I would have been 3 by 3. Some matrix. I just put numbers here, but we also don't know the element of. We also don't know. Well, we know A. We just don't know lambda. So look at it as a matrix equation. Now, what does this tell me? If I have this one that is equal to 0, this tells me that probably most of you don't even remember this, again, depending how much you deal with it. But this tells me that A minus lambda I is singular. It's a singular matrix because it's equal to 0 here, right? Singular matrix. Now, this, some of you might remember, what is one property of a singular matrix? What was special about singular matrix? Do you remember what was something that we cared about singular matrix, or something that we were aware of? Yeah, it's old knowledge probably. What we know about singular matrices is that their determinant is equal to 0. If you remember, we couldn't find the inverse of a singular matrix easily, and the problem was the determinant was 0. So once you have a singular matrix, and we know it's singular matrix, this comes out of it. Determinant of this matrix, A minus lambda I, is equal to 0. And this is what we have been looking for. This is the golden, I don't want to say rule, but something we care a lot about. You have to find the determinant of A minus lambda I. Now, what comes out of this, we're going to look at an example, is the characteristic equation or eigenvalue equation. Gives you a polynomial that its roots are eigenvalues. So let me write it. Characteristic equation. Characteristic equation. Or eigenvalue equation. Eigenvalues or eigenvalue equation. You can call it either. All right. So that's how we find eigenvalues. How do we find eigenvectors then? Then once we find eigenvalues, right, the roots of this equation, polynomial, are going to be eigenvalues. Once we find eigenvalues, we plug in eigenvalues into this equation right there. And find eigenvector associated with each eigenvalue. I'll show you how, and you've done it, but we're going to go over a simple example to remember or refresh your memory about how to do it. At this point, you want to ask, what does it have to do with vibrations? Well, you have to be a little patient. In one class, not today, maybe hopefully next class, you'll see the connection. Or maybe it takes a little longer. We'll see what is our pace. But just as a hint, that these eigenvalues and eigenvectors, later on, when we start looking into systems with more degrees of freedom, eigenvalues become, they're tightly related to natural frequencies, and eigenvectors are tightly related to mode shapes that I'll define later. But just keep that in mind, that we're going to use this procedure to find eigenvalues and eigenvectors, and they start having physical meanings in vibrations, right? All right, so let's take a look at an example. How can we calculate this? Very straightforward one. Let's say we have a matrix A. Find eigenvalues and eigenvectors for 2x2 matrix. It has to be a square matrix, but it can be 3x3, 4x4, depending on what your application is. But we're just going to stick to this. It's also a symmetric. So when we have a symmetric matrix, which pretty much all the matrices we're going to deal with in vibrations in this course are symmetric. Right? So when you have a symmetric matrix, what is symmetric matrix? all the non-diagonal elements, right? If you look at the draw a line there, all the non-diagonal elements like are similar, right? From also 2 by 2, so pretty much the element that you have at, let's call this A1 2 is the same as A2 1. Well, it's symmetric. Now, what is good about symmetric matrices is that, well, eigenvalues are always real eigenvalues. Eigenvalues, as I said, can be positive, negative, or zero. But keep in mind that eigenvalues can be complex numbers. In a general scheme, that in linear algebra, when you find eigenvalues, depending on what your matrix is, those eigenvalues can be real numbers, can be complex numbers. But when your matrices are symmetric, it's guaranteed that your eigenvalues are always real. So that's a good thing. They're positive and they're real. You don't need to worry about that, but just heads up that if you get an eigenvalue that is negative or it's not real, it's a complex number, within the scope of this course, something went wrong somewhere. Right? All right, so here's the matrix. Let's do what I said we are going to do. Right? Let's find the determinant A minus lambda I is equal to 0. Here's what I'm going to do. Determinant of A, which is 3, 1, 1, 3, minus lambda 1, 0, 0, 1 is equal to 0. So that would be determinant of 3 minus lambda 1, 1, 3 minus lambda is equal to 0. How do we find the determinant of a 2 by 2 matrix? Well, these two, I'll multiply them together. 3 minus lambda squared minus 1 is equal to 0. As a reminder, if you do not remember and you're too shy to ask, reminder, determinant of a 2 by 2 matrix, if it's A, B, C, D, was AD minus BC. That's how we were finding the determinant of a 2 by 2 matrix. So just keep it there in case you don't remember. Right? All right. So AB times CD, A3 minus lambda squared minus 1 is equal to 0. You can expand this. I have to find the roots, right? This is supposed to give me an equation. So that would be a 9 plus lambda squared minus 6 lambda minus 1 is equal to 0. This gives me lambda squared minus 6 lambda plus 8 is equal to 0. It's a polynomial, second degree polynomial. You can find its roots, right, easily. From there, I can actually, I'm going to do a trick. I'll write it as a multiplication of two expressions, and that would be 2 and 4. But they should be negative, so summation of them would be minus 6. I do it, but you can just find the roots if you don't feel comfortable doing this. So this means lambda 1, I'm going to call it lambda 1. The first root is 2, and lambda 2 is 4. So these are the roots of the characteristic equation. Characteristic equation is supposed to give me eigenvalues, and the roots are obviously eigenvalues. So these are eigenvalues. These are my eigenvalues. Any question about this, folks? Now that I know eigenvalues, I can find the eigenvector associated with each eigenvalue. So I'll say for lambda equal to, or for lambda 1, let's go with lambda 1 equal to 2. I'm trying to find eigenvectors now. Let's see how do we do that part, and how can we find eigenvectors. Going back, I told you this is the equation you have to look at. A minus lambda I times x. And those x vectors are going to be our eigenvectors. So here we'll say, well, where is, so A minus lambda 1, I replace lambda with lambda 1, is equal to x. And since I'm finding the first eigenvector, I'll just call it 1 is equal to 0. It's not general x anymore. This is the first eigenvector. So just plug in the numbers. A minus lambda 1I would be 3 minus lambda 1. Minus lambda 1. 1, 1, 3 minus lambda 1 times, well, x is a 2 by 1 vector because the matrix is 2 by 2. This becomes x 1 1, the first element, and x 1 2. It's equal to, if you want to write it very complete, 0 and 0. It's a matrix operation. Let's see what happens there. So if I plug in lambda 1 is 2. So that's what I get. 3 minus 2 is 1, 1, 1. 3 minus 2 is also 1. Right? All of these are 1. Multiplied by x1, 1 and x1, 2. These are elements of the first eigenvector. It's equal to 0, 0. What does this give me? I can write it. Right? It gives me two equations. I'm looking for x1, 1 and x1, 2. Two elements of the first eigenvector. If I write it, x1, 1 plus x1, 2 is equal to 0. Right? The first row, I'm multiplying the first row with the column. Right? It's a multiplication of 2 by 2, 2 by 1. So 1 times this one and 1 times this one. It's equal to 0. Becomes the first element. Is equal to the first element. Right, to the right side. For the second one, right, I'll do, well, the second row multiplied this multiplied to this one and this multiplied to this one is equal to this element. So that will give me x1, 1 plus x1, 2 is equal to 0. All right. I have two equations, two unknowns, but you see that's kind of strange because doesn't give me that much information there. It just pretty much tells me this is it. Now figure out what is x1, 1 and x1, 2 is. By looking at this, you feel like, well, I can put 0, which is, again, it's a trivial solution we said we're not interested in. That's the interesting part. Eigenvectors, you can see that this is not unique. There is no unique solution to this. If I take x11 as 10, then x12 should be minus 10 to make this work. If I take x11 as 100, x12 should be minus 100 to make this work. So any number I take, x12 should be just the negative of that number. This becomes 0. So here is the general procedure. Right? You will face this situation almost always when you're finding eigenvectors. What do? You take one variable as the free variable, as they call it, and give it a number, assign it a number. Either x11 or x12. Just take it as free variable. I'll take x11 as the free variable. Right? Take, let's say in this case, x11 as free variable, meaning that I can assign it a value. And I'll say, well, x11, let's take it 1. I might say, why did you take 1? That's the general, I would say, routine or standard that we go with 1. It's the simplest number we can assign. I could assign 1,000, 10,000, 1 million, whatever you want. You could assign 0.0001. It's still correct. But the standard way, and you will see later on, it's easier to visualize or think about the effects, especially in vibrations. It's just take one of them as free variable and assign it, I would suggest always 1. So take x11 as free variable, I did that one, and assign it 1. So what happens? If I do that, then x as vector becomes, well, x11, I assign it 1. Any of these equations gives you x12. You take x11 to the other side, x12 is the minus x11. It would be minus 1. This is your first eigenvector. First eigenvector. The eigenvector associated with lambda 1. Right. So we found eigenvalues by finding the roots of polynomial, and then for each eigenvalue, we're finding eigenvector. So we do the same process for the second one. Second eigenvalue for lambda 2 is equal to 4. Right? Let me double check if it was 4. Yes, it was 4. I'll say a minus lambda 2I times, in this case, x2 is equal to 0. So that would be 3 minus lambda 2, 1, 1, 3 minus lambda 2 times x2, 1, x2, 2 is equal to 0, 0. Now lambda 2 is 4, so this becomes 3 minus 4, becomes minus 1. 1, 1, and 3 minus 4 would be minus 1. x2, 1, x2, 2 is equal to 0, 0. Right? Write it in the form of 2 equations. Again, first row multiplied by the column gives you the first equation, minus x1, x2, 1 plus x2, 2 is equal to 0. And the second one gives you x2, 1 minus x2, 2 is equal to 0. Now here you see there's a different relationship between x1 and x2. x2, 1 and x2, 2 are equal. If you take one to the other side, both equations, either of these equations gives you the same thing. Right? It's the same. But again, it can be any number. 1, 10,000, 10,000, 1 million, 1 to 10 to minus 10, any number. But we do the same thing we did. Take 1 as free variable, take 1 as free variable. I'll take I'll do the same thing. I take this as 1, just to be consistent. We could do anything. It doesn't mean that because this is what we did in the first, for the first lambda, we have to do it for the second lambda. Still, you're free to choose any number. But always try to go with 1. That's the easiest one. If you do that, and then x2 as a vector, well, x2, 1 is 1, and then x2, 2 becomes minus 1. Either of those equations give you this. So this is the eigenvector, or the second eigenvector. Second eigenvector. Eigenvector for lambda 2, or associated with lambda 2. So that's it. We found eigenvalues. That's the typical procedure you follow. We found eigenvalues. For each eigenvalue, we found the eigenvector associated with that. Now, later on, you will see how does this materialize itself, or how do we give meanings, physical meanings to these, and how do we use these in vibrations for more complicated system? How do we use this to solve the equation of motion for more complicated system? All right. All right, so that's it. I'm going to close this topic, eigenvalues and eigenvectors. I just wanted to refresh your memory, remember what they were, how do we calculate them. Any question about this, guys? All right. Let me have there. I don't see any question. All right. All right. We'll get back to this and we'll use this later on when we're dealing with systems, more complicated systems. One more thing before we dive deep into more complicated systems is the concept of degree of freedom. Make sure that I told you everything I wanted to say. Yeah, I think we're good. The concept of degree of freedom, what that is and why is it important? So degree of freedom. Of freedom. At least in mechanical engineering. You see degree of freedom in other majors too, with a little bit of difference, obviously, in definition and the application. Degree of freedom. Now, let's start with the systems we've been dealing with. All right? Think about the spring mass damper system. I'll ignore the damping because it doesn't really do that much in this context. Let's just think about the spring mass system. Right, this is K and that's it. Remember, when we were solving the equation of motion for this, or when we were writing the equation of motion, everything, we were finding a system response. What was the system response? It was pretty much just some xt, right? If this is the equilibrium point, it was pretty much some xt telling us where this mass is. So as long as we could find some xt telling us where this mass is at any given moment, right? As long as we know the moment and we could find the system response, we could say where this system is at any given moment. That x value was enough to describe or to tell us where this mass is at any given moment. We didn't need to know any other variable. X was enough. And what was x? X was the displacement from the equilibrium point. All right. As long as we knew x, we could fully describe the motions, the system's motion. I could just say, well, at this time, I know x. So at any given time, you tell me, this is the x, and this is exactly how the system is system's behavior. We didn't need anything else to describe the behavior or the motion. Right? Now, this is a system with 1 degree of freedom. Right? When you need only one variable, one independent variable, if you want to be more accurate, to describe the motions or the system's motion, it's a 1 degree of freedom system. So this is 1 degree of freedom, meaning that you only needed one independent variable to describe its motion. So one called DOF. Mainly I'm going to refer to this as DOF, degree of freedom. Now, you tell me, how about this one? What if we have a mass there? It's connected by a rod. This rod is welded or is connecting these two, so they move together. Right? Think about the rod welded to two masses, and these masses can, as a result, move together. The spring there, okay. How many variables do I need to fully describe this motion? Right? What do I need to know? Do I need more than one x? Do I need more than one variable, independent variable, in this case x or whatever you want to call it, to describe the motion? Can someone answer this? Think about this. The way you can think about this is that you have two masses. Now, if I know where this mass is at any given moment, like some x, is it enough to fully describe this motion? Is it enough to exactly know where everything is, where both these masses are at any given moment? Do I need to know more, or that's enough? How can you approach this? You can hold one mass, that's a rule of thumb, and see if you can move the other one. Can we do that here? This is the most quiet class I have among all the classes I teach. No message on the chat box, no comment, no question.
Well, aren't the masses moving in unison since there's a rod attached to them?
Exactly. Thank you, Dominic.
You're
So
welcome.
they are attached with a rod. So they are just moving together. So this is also 1 degree of freedom system. It's 1 DOF. Because as long as I know x, that x could be either x for this mass, can be an x for the other mass, can be an x in the middle of this rod, anywhere. This is a rigid body. Think about it. They're attached together. They move together. So it's still 1 degree of freedom. I need only one independent variable to describe this motion. Now let's look at this one. M is attached there. K with another spring attached to this mass. How about this one? And let's call them, for the sake of argument, M1 and M2, so it's easier to refer to them. How about this one? If I move M1, if I know where M1 is at any given moment, do I know where M2 is? As knowing nothing about M2, just knowing the position of M1. Is that enough to describe this system at any given moment?
No, since the masses are independent of each other's motion.
Exactly, Anton. Thank you. So exactly as the way he said it, they are independently moving, right? It's not a rigid body anymore. If I hold M1, I can still move M2. So now I need two variables to define this or describe this motion. M1 can move, and M2 can independently move also. So 1x is not going to be enough. This is a system with 2 degrees of freedom. I need two independent variables to define its motion. Other examples. Let's take a look at this. Well, following this explanation, you can get a system with 3 degrees of freedom. M1, M2, M3. Right? Let's call this K. Let's go with K1, K2, K3. Now, in this case, I need 3 because each of them are independent. This would be X1, this would be X2, and this would be X3. They are not dependent on each other. When one moves, the other one does not have to move necessarily. Right? So I need to know the position of each of them separately to be able to fully describe the motion of this system. All these 3 are moving, but knowing the motion of one, I cannot say anything about the motion of the other 2. So this is 3 degrees of freedom. So let me give you the formal definition. Right? Let's write it this way. The minimum number, the minimum number of independent variables are required to fully describe, oh, I don't know what did I write right there. Describe a system's motion. I can give you some other examples. The famous, some of the interesting ones. Let's say I have a pendulum like this, mass M, and it's swinging around this point. What do I need to know? What is the minimum number of independent variable required to fully describe the system's motion? We studied this, right? What did we have to find to fully know where this system is at any given moment? All right. We needed to know theta. Here is theta. As long as we knew theta, we could just know where this pendulum is at any given moment. So that's also 1 degree of freedom system. Now, what would be the pendulum with 2 degrees of freedom system? Oh, there you go. This is one link there connected to another one. And then we have mass M there. In this case, you need to know this theta, or let me just be consistent with colors. You need to know this theta. I'll call this theta 1. And you need to know the other theta. These are at least number of variables you need to know to fully describe this motion. So this is 2 degrees of freedom. Now, keep in mind, we're talking about minimum number of independent variables. In this case, you could say, well, I think we need 2. If I put my coordinate here, X and Y, I need to know where this is at any given moment. Let's call this X1. Use something different. Let's call this Y1, and this is X1. This is 2. I need to know X and Y. But X and Y are not independent, right? If you can actually write them, they are dependent. You can say tangent theta is equal to Y1 over X1. You see, they are not independent, they are related to each other. So The independent is important here. You need minimum number of independent variables. Another example of degrees of freedom. Let's think of this. This is for you. You tell me if I have spring there, mass 1, goes through something like this. Mass 2. The pulley is there. And this is hanging by a thread. What is the degree of freedom for this one?
Two degrees of freedom.
Good guess. Which, if you really want to go into details, it might not be exactly. Sorry, go ahead.
Height of M2?
Well, you just need one. So pretty much one is enough. If you look at this, if I know where this is, at any given moment, let's say this one is here. They're connected together with a rope, so there is no spring between them.
So this is similar to the one we did before with the rod in between, because it's still the same amount of displacement, but it's just direction.
Exactly. So still they're connected. So as long as you know one, you're good. This is one DOF. It's actually what you said. But it could be two DOF if we had this case. If we had M1 going over there, and then there was a spring there, M2. In that case, this could have been a 2 degree of freedom. This is a 2 degree of freedom because if I know where this is, doesn't mean I know where this one is, because there's a spring there. If I hold one, think about it, if I hold M1, I can still pull M2 because of the spring. So now I have 2 degrees of freedom for this case. All right. Hopefully you get the idea of degree of freedom and what it is. The formal definition gives you a pretty good or I would say guideline, but you have to be very careful about how to interpret that and how to actually look at each independent variables. All right. Now that we know this, let's talk about systems with 2 degrees of freedom. So far, based on what you realize, what I draw here, every system we talked about, we converted that system into spring mass damper, spring mass. Every system we talked about was just 1 degree of freedom. That's why we didn't talk about degree of freedom. Everything was 1 degree of freedom. Now we're going to higher degrees of freedom. Specifically, we'll be focused on 2 degrees of freedom, 2 DOF. But whatever we say for systems with 2 degrees of freedom can be applied to systems with multiple degrees of freedom, 3, 4, 5. It's just matrices become bigger and more complicated. So that would be pretty much what we'll focus for the rest of the semester. Systems, we'll see when we talk about vibration absorbers. They are systems with 2 degrees of freedom under force vibration. So systems with 2 degrees of freedom. I'm going to look at their equation of motion, obviously. As always, we start with the system that just the spring mass. And what I'm going to do is that I'm going to derive the equation of motion for a very general form. Right? I'll say I have 2 masses there. It should be very similar as much as it possible. Right? Let's say they're connected together with a spring and a damper, most general form. Let's call this M1, call this M2, and then this is connected to a wall by another damper and a spring. So let's go with another damper and a spring on the other side. It's the most general format. Let's call this C1, K1, C2, K2, and C3, K3. Two masses attached to each other with the springs. I added dampers there to make it more general. And even we can go further and make it more general of case by saying that this one is under a force F1T and this one is under a force F2T. Similar to force vibration we had. This is a 2 degree of freedom spring with the spring and dampers under force vibration. See how can we derive the equation of motion for this? Since we have 2 degrees of freedom, we have to look at each degree of freedom separately and draw the free body diagram for that. Go all the way back when you were you had dynamics or statics, when you had systems with 2 components or multiple components. Think about rigid bodies with multiple parts. What were you doing? You were dismantling and drawing free body diagram for each part. And you were taking into account the interaction or the internal forces, the forces between components as well, aside from external forces. So we're going to do the same thing here to draw a free body diagram. Now, there is one important, I'll tell you, you'll see why, important assumption you have to make at the beginning. Right? It's a 2 degree of freedom. So if it's 2 degree of freedom, this would be x1 and this would be x2. We need 2 variables to describe this motion. Right. I'm sorry. X1 and x2. Right, we already know it's 2 degree of freedom. We need 2 independent variables. I'll call the motion of M1 x1, the motion of M2 x2. Remove it. Now, the assumption you have to make is that what is the relationship between these 2 motions? Is one greater than the other or not? Or is the opposite? That assumption does not change anything when you derive the equations of motion. What you have to make the assumption to be able to draw the correct free body diagram. So very important. Here I'm going to assume that x1 is greater than x2 at some given moment that I'm drawing the free body diagram. Right? It's a very important assumption. When you deal with systems with multiple degrees of freedom, you have to make the assumption about displacements or the relationship between the motions of each degree of freedom at the beginning. So x1 is greater than x2. That's my assumption. Does it matter if I go with x2 greater than x1? Not really. You should get at the end the same set of equations of motion. Now, let's start with the first one. Let's start with free body diagram and let's just write mass 1. This is easier. Mass M1. Here is mass M1. I separate that. Let's say this is the free body diagram of that. Now, pay attention to the process here. M1, and I said x1 is greater than x2. When I make that assumption, right, let's just start with the left side. We have K1 and C1. So M1 is going to the right. Right? I made the assumption about directions and the relationship between these variables. If I didn't mention that, you also have to make an assumption about the direction. And almost always take the assumption as they move in the same direction, just for the sake of getting the right equations of motion. They go in the same direction, just make the assumption which direction is that, and make the assumption of which one is greater than the other. 2 things you have to pay attention at the beginning. We set that right, then we start looking into free body diagram for each degree of freedom. So M1, X1 is going to the right, or M1 is going to the right. What should be the direction for the forces applied to M1 because of K1 and C1? Right? So both of them are in equilibrium at the beginning. M1 is going to the right. What would C1 and K1, or the forces caused by C1 and K1, do? Or how would they be applied? How should we apply them on M1?
So we would want to move M1 back to the equilibrium position.
Exactly. They want to move it to equilibrium position. Thank you, Chris. It was Chris, right? We want to take it back to equilibrium position. So this go this way, and this was go this way. K1, X1, and C1, X1. They want to take it back to equilibrium position, and the motion of M1 is X1. We also have F1T, that is an external force applied to the system. We already know that, so I'll put it here. Here is the tricky part. For the spring and mass, springs and dampers between two masses, I made the assumption that X1 is greater than X2. Listen carefully to this. There's a lot of mistakes happen here. I made the assumption that X1 is greater than X2. Now, if X1 is greater than X2, it means, if you want to think about it, think about M2 is fixed and M1 is moving to it. Right? Whatever the difference is, you can think about that. Since X1 is greater than X2, both of them are moving, but X1 is moving slowly, X2 is moving faster, right? You see that? If they start at this distance, let's say, perpendicular to camera, there you go, like this. And then M2 is moving, M1 is also moving, but M1 is going faster than M2. It's getting close to M2. Which means that the spring and damper between is going to push M1 back. They are compressed. Right? As I usually say, to imagine the correct direction for C2 and M2, or the forces caused by C2 and M2 applied to M1, think about whichever is the smaller motion, in this case X2, is fixed, and whichever is the larger motion is moving. That might help. Think M2 is fixed, because X2 is smaller, M1 is moving. So it would be the same situation as the wall situation. Spring and damper want to push this M1 back to its equilibrium. That would be this way. Now that we figured out the direction, what do we do about the magnitude of the force? Well, here is what you do. C2 and K2, well, these are there, multiplied by. What is the amount that K2 is compressed? And always go with positive, because we already decided about the direction. So we want a positive number as the magnitude. What is the amount that K2 is compressed? If M1 is getting close to M2 with X, or X1 going this way, X2 going that way, and X1 is greater than X2. How much is the compression amount for spring K2, assuming that everything is started from equilibrium? Right. This is a relative displacement, right? If this is X2 and this is X1, the amount that this spring is compressed is X1 minus X2. And it really depends on the assumption you made X1 whether X1 greater than X2 or X2 greater than X1. You always keep this magnitude positive, and this one becomes X1 dot minus X2 dot. This should be also X1 dot, right? For the previous one, it's a damper, force of a damper. So I decide about the direction. That's why that for initial assumption is important, X1 greater than X2. I made the assumption about the direction. Gets close, right? This is pushing back, Right? The one that is smaller, assume that it's fixed, so spring and damper are pushing back. The direction, we can decide that way. And the magnitude, keep it always positive. Remember, it's a relative motion. Now that's pretty much all you need to have on your free body diagram. Then on your kinetic diagram, you will just get M1, and it's going this way, so that would be M1 X1 double dot. Pretty much that's the acceleration of your mass. Now we can write the equation of motion. Summation of forces would be M1 X1 double dot. We're just looking at this specific mass. I'm going to take the right as positive. So that'll give me minus C1 X1 dot minus K1 X1 minus C2 X dot 1 minus X dot 2 minus K2 X1 minus X2 plus F1 is equal to M1 X1 double dot. Just expand this. The rest is just playing around with this equation. We'll get M1 X1 double dot. I'll move everything to the other side, plus C1. If we take X1 dot out, that would be C1 plus C2 X1 dot. I'm taking factoring X1 dot together and moving it to the right side. So this becomes C1 plus C2 X1 dot, and then we'll get minus C2 X2 dot, and we get to springs plus this becomes K1 plus K2. If I'm not wrong, K1 goes to the other side, K2 X, this is X1, and then we have minus K2 X2, positive goes to the other side, becomes negative. This is equal to F1, and this is F1T. I have to write it correctly. So this is the equation of motion. It's not the color I was going for. This is the equation of motion for the first mass. Equation of motion for mass M1. Right, and we can do the same thing for mass M2. I'll do it in the next class, but we can do the same thing for mass M2. We're going to get two equations now. This is the difference. We have 2 degrees of freedom, so we're going to get 2 equations of motion. And you will see we write it in a matrix form. And that's where the whole how to deal with matrices and find eigenvalues and eigenvalues and eigenvectors come into play. Now, there are 2 ways of solving these equations of motions. Once you get 2, put them in matrix form, you can either solve it directly, as long as it's harmonic motion, and you just give it some initial velocity or displacement. Think about the free vibration for 1 degree of freedom we were looking at. You can just use the direct method, or you can use model analysis technique, which model analysis is going to be the one I'll be more focused on. And as I said, this part, the way we follow is a little different from notations. The way we solve it is a little different from your textbook. So I highly suggest that you follow what we do in the class to be able to actually do the problems and solve the problems the way you should. All right.